Apache Kafka operates at a staggering scale. Modern deployments process trillions of events daily, serving as the central nervous system for enterprise event-driven architectures. Welcome to The Anatomy of a Bottleneck, an architectural deep dive produced in partnership with Royal Research. When you push that volume of data through any distributed system, localized bottlenecks, both logical and hardware-based, are mathematical certainties. When a single node struggles, the surface-level symptoms manifest almost instantly. Data streams back up, read requests stall, and critical analytics pipelines go dark. Maintaining high availability requires moving past reactive firefighting. You need a mechanistic mental model that maps those surface-level logical symptoms directly down to the physical limits of your infrastructure. We call this framework the observability hierarchy. Diagnosing failures accurately requires looking at the cluster through three distinct operational layers. This diagram outlines the three-tiered stack. At the top tier is the logical data layer, which governs how your data is distributed, categorized into topics, and consumed. Below that is the broker hardware layer. This represents the physical constraints of the specific machines running the cluster, namely their CPU, memory, and disk I/O limits. At the foundation sits the coordination layer, responsible for maintaining the cluster state and managing the fallout when a broker fails. Industry-standard tools like Prometheus, Datadog, and Confluent Control Center are built to aggregate metrics across these three specific tiers. True root cause analysis means pulling data from these platforms and correlating anomalies vertically through all three layers simultaneously. This visual represents a topic partition queue. Consumer lag is the exact numerical difference between the latest message offset generated by the producer and the current offset successfully processed by the consumer application. In a healthy state, event consumption is nearly instantaneous. The consumer offset closely trails the latest offset. But in a degraded state, the producer continues writing at high velocity, advancing the latest offset, while the consumer offset stalls. That growing gap is your lag. The common assumption is that the consumer application simply lacks the processing capacity to keep pace with the incoming data stream. However, lag is frequently a downstream indicator of upstream cluster degradation. The consumer might be starving for data because the cluster is struggling to serve it. Before you automatically provision more consumer instances, you have to investigate the internal cluster metrics. Consumer lag is merely the symptom. To find the disease, we step down one layer to examine how data is partitioned across the individual brokers. Here we see the logical architecture. Kafka divides topics into partitions and distributes those partitions evenly across multiple broker nodes to balance the load. A condition known as partition skew occurs when data routing rules unevenly assign the vast majority of incoming traffic to a single partition. You end up with several broker nodes sitting completely idle, while one broker is absolutely hammered by data. That overwhelmed broker reaches a physical limit. It can no longer process incoming log appends fast enough, forcing producer requests to queue up. This localized queuing delays the availability of new messages to the consumer. The consumer isn't slow. The data is trapped in a bottleneck, artificially inflating the consumer lag metric. We can confirm this by checking a secondary logical metric, replication. An overwhelmed broker will often fail to replicate its data in a timely manner. This triggers an under-replicated partition warning. It explicitly indicates that copies of your data are no longer in sync, exposing you to potential data loss. Partition skew tells you exactly where the failure is occurring. But to understand why that specific node is failing, we must drop down to the physical hardware constraints of the broker itself. Let's isolate that single overwhelmed broker and look at its physical hardware. This dashboard tracks the broker's physical limits. Kafka ensures data durability through sequential disk I/O operations to append logs. When disk write speeds saturate, read and write operations bottleneck. The broker physically stalls and can no longer accept new messages. If the disk isn't the limit, check the RAM. Excessive buffering rapidly exhausts available memory. When depleted, the JVM triggers intensive garbage collection. These GC spikes create long pause times that temporarily freeze all broker operations. Finally, Kafka requires massive network bandwidth to handle incoming client traffic and internal data replication simultaneously. Saturated network lines create hard latency. If the pipe is full, message replication to follower brokers simply cannot occur in time. These three physical bottlenecks, Disk, memory, and network are the root causes driving the partition skew and consumer lag we saw at the logical layer. When any of these hardware components saturate, the broker essentially goes deaf, and a deaf broker triggers an immediate crisis at our final layer, coordination. The coordination layer is responsible for monitoring the health of all brokers and managing partition leadership. Here we see a traditional setup where Zookeeper acts as the external metadata manager. It tracks broker health by listening for continuous heartbeat signals from every node in the cluster. When a broker is paralyzed by hardware saturation, like a prolonged JVM garbage collection pause, it stops sending those heartbeats. This results in session expiration. Zookeeper registers the timeout, officially declares the unresponsive broker dead, and routes new connections away from it. This triggers a leader election. The cluster promotes in-sync replicas on healthy brokers to take over leadership of the failed partitions. Modern versions of Kafka, starting with 2.8.0, offer craft mode. This architecture internalizes the metadata quorum directly into the brokers, removing the external Zookeeper dependency entirely. Regardless of whether you rely on Zookeeper or Craft, monitoring coordination latency is critical. It guarantees your cluster can accurately detect hardware failures and seamlessly self-heal. Diagnosing the exact layer of failure allows you to implement targeted mitigations that actually resolve the bottlenecks. You resolve partition skew at the logical layer by actively rebalancing topic partitions, establishing an even distribution of data across all available brokers. To mitigate disk exhaustion at the hardware layer, configure aggressive log cleanup policies and retention settings so the system automatically deletes old data before the drive fills. You must also allocate dedicated network lines exclusively for Kafka traffic. This eliminates competition for bandwidth and reduces internal replication latency. Finally, perform periodic broker upgrades. Moving to the latest stable release ensures you benefit from optimized memory management and critical security patches. Applying these physical and structural mitigations eliminates the root hardware constraints, causing logical symptoms like consumer lag to naturally drop back to zero. A healthy Kafka environment requires moving from a posture of reactive troubleshooting to one of proactive capacity planning. Sustaining growth means anticipating future load and regularly validating your configurations through automated testing before the system hits its limits in production. Effective troubleshooting is an exercise in strict layer isolation. You must correlate logical software symptoms down to their physical hardware constraints and verify how your coordination layer responds. Mastering this observability hierarchy is the only way to guarantee high availability and reliability for a large-scale event streaming architecture. Thank you for joining us for this architectural deep dive, brought to you in partnership with Royal Research.